Hello, my name is Cody Rogers, and today I'm going to be given a short overview of the test results from my dusk-to-dawn transistor project. Right now, I just want to go through the results that I got from measuring with the PPK2. I will be posting a full video, like the full measurement saga per se, but it's gonna be like 1 hour of total video. So I just wanted to make a shorter video for those who don't really want to watch that entire thing, where I just go through the results. First, I will show you. So here they are. This is the spreadsheet I used to record it on. I'll take a screenshot of this and put it at the bottom for the rest of the video, but this is what I'm going to be working on, like when I'm talking. So to start off with, we got J1 here. So this connector right here. I expected that when it was dark, that it would have 1.224 milliamps going through it. The measured value was actually a little bit higher. It was 1.37 milliamps going through this. Now for the expected value in the light, I expected 1.147 milliamps, and it was actually 0.241 or 241 microamps. So both values were a little bit higher than I expected. Now we'll go down just here because it makes more logical sense. It will skip around a little bit, but we're going to go down to J4, so the current going through R1 here. So that I expected 35 microamps in the dark, 35 microamps in the light. Now, it wouldn't change because no extra current could go through. It's always just basically 3 volts starting here through this 68 kilo ohm resistor down. Some goes into this collector, and some would go into this base down to ground. So we have a diode drop and then that resistor. So I expected 35 microamps. The calculation, I think I'll post another video. I did go through the calculations that I had on the whiteboard, so that may also be included at a later date. But we're just gonna talk about the results here. Then what I got was in the light, so when the light is on, 34 microamps flowed through here. And when the light was off, 33 microamps flowed through. Now I think there was a slight drop because of the draw on the battery, would be my thoughts. I'm not sure though. That's just a guess that the battery is getting taxed a little bit more, so its voltage would be showing less, which then would result in like that tiny. It's a small amount, like 1 microamp, so it's almost not even worth thinking about. But I'm guessing that's why. So now let's go down to J2 right there. So J2, I expected the same amount, 35 microamps. We actually saw slightly more both times, 36 microamps in the dark, 37 microamps in the light. The reason for that, I don't know. I don't really have a good reasoning for it. I'll have to think about that more. But we'll head on to J7. So this one right here. It was expected to have 35 microamps in the light. So when this resistor value is very low, then this would have a high voltage and there would also be lots of current flowing through here, which would saturate this transistor pair, which would cause it to deliver all the amperage needed to match the amperage over here. Yeah. In the dark, this resistance goes way up. So that means the voltage here is much lower, and the current here is much lower, which turns off in the dark. This pair is turned right off, so no current is flowing through. So 0 microamps. What I measured was basically exactly what I said, but considering that what we measured here at J2. So we saw 37 microamps through J7 in the while lights were turned on, and 0 microamps in the dark. Now over here at J3, basically would be the opposite. In the dark, it should be conducting all the current that would be going through J2. And in the light, it should have basically 0 microamps because this side of the circuit would hog it all. And that is also what we see. Yeah. So we can go down at J5 here. Would be basically the same thing as J3. And that is what we see too. Or that is what I recorded. Now here at J6 is where we get some more of why we get why we saw a little bit higher power draw was because of this guy here. So we saw 1.09 milliamps going through it when we expected about a milliamp. And we saw, well, yeah, that's only 160 nanoamps, so it's not enough to compensate for what we thought was the expected value going through from the battery. But anyways, we thought there would be only 0, like there would be no current going through here, but there was 160 nanoamps. Again, hardly worth mentioning. But let's go and talk about some of the more interesting parts. So this was a question I wrote for myself in my notebook. If it is somewhat light, almost dark but not quite, J7 should have some current. Remark on both the current through J7 and J3 in this situation. So in the full video, you'll see I cover the photoresistor with my hand, trying to not drop its, not change its value too much. And what I found was that I can make it go up to 5 microamps flowing through J7 while this LED is still on. Now for J3, I did the same thing, and I found that I could get its current down to 25 to 30 microamps. J5 I could have 5 to 30 microamps. It was quite often. Now J6 was a much different situation. It was a very fuzzy photo going up and down, and I couldn't pin it at all. I couldn't make it just have a nice smooth thing. It was either wanting to be have current going through it or not have current going through it. Now there's 2 things I did. I added a test point in 3 different places. I added one here so I could measure the current going through this photoresistor. I added one here. Yeah, I think I did. I should have added it here actually. But anyways, I added it here. Then I added one here too. So what I found was in this one, in the light, it was 91 microamps flowing through here. In the dark, it was only 6 microamps. And over here, it was in the light, 30 microamps flowed through here. And in low light, 10 microamps or less. Otherwise, the LED was off. So I could, basically what I'm saying there, I could have about 10 microamps flowing through there without the LED turning off. Now over here, Q1C, I had in the light, there's 85 nanoamps, so a tiny amount of current. In low light, there was 2.5 microamps. And in dark, like when it was dark, there was 0. So this does make sense. I'm just going to give my explanation for it now. I've found that it is a lot better to think in terms of currents with transistors. If the current through here is going to be very, very little, then that means there's going to be very little current going into this space. Now, what eventually puts it into cutoff is that this voltage does go down to the point where there's no way that anything can flow through here. However, if we don't have much current going in anyways, then that means this isn't going to be driving much current through here. So then that is why some current can be flowing through here. So it's not in cutoff yet, and this LED be on. Now, eventually, what happens is that when there's no current flowing through here, that means there's no current flowing out of these spaces, which means they're in cutoff, which means that this output basically will sink as much current as it can to try and meet the requirement over here, which that is when the LED is turned 100% turned on. There was some other things, like when I unplugged the short over here, this LED would turn on. That's again, that gave me some intuition. Too, I think that while I pull this out, that means that there's no path to ground here, so there's going to be no current flowing. That automatically turns this off, which then forces all the current to come through here again. But if you want to hear all that, see all that, it's probably best if you just go watch the future videos, and I hope that you do. And thank you for listening to this video.